Okay, another separate video on this is on indices. So I will mess up this this right up here a little bit, and let me comment on those indices. And let me comment on this, why we have this 2k, why we have lambda k here, why this is useful. First of all, it's worth your time for all this Gaussian fermionic business to see how this plays out. So we are summing over the blocks. The next slide will be about the blocks. And we start with k equals 1, which means lambda 1. And then for k equals 1, 2k minus 1 is 2 minus 1 is equals to 1. Okay? And then 2k is equals to 2. And that's your starting point. And that's where you know that, okay, I will always start from 1 until the upper border, which is L or 2L. And I will always start with 2k minus 1 because 2 minus 1 gives me the first Grassmann number. So this is the 2k minus 1. And the next one is just 2k, you just write it blindly. And then the second one, this is k, this is 2k minus 1, and this is 2k. So k equals 2, then 4 minus 1 is 3, and then 4 is 4. Yeah. So those are the indices. So, okay. And let me now explain one more thing. It's also worth the exercise. What happens if I'm taking a product? Notice that if I'm writing a product, I'm always writing a product of commuting quantities, lambda k. And then I will have here g2k minus 1 and g2k. So now let's try to make an exercise to connect this with lambda, and in particular, let's check the sign. So I think in the session, I was writing k from 1 until here, and 0, lambda k, and here I was putting the minus. So let's see whether this will work out. First of all, it's block diagonal. So we should get comfortable with saying that k j is 0 if k minus j is not equals to 1. Okay, so something like this, which means that they can differ only by 1 because we have those blocks, but also they have to be even blocks. So this will be a matrix with 0, minus lambda 1, 0. And then another block will be 0, minus lambda 2, 0. And then it will continue. Okay, which means that I need to be able to select, if this is row 1, 2, 3, 4, I need to select pairs of an odd number and the next number, which is 2. And that's exactly what this numbering does. 2k minus 1 and 2k. Those are the pairs. So so what does it mean? It's this 2k minus 1 and 2k, they differ by 1. And otherwise it's some number. Yeah. And a more precise way to write it is that the only matrix elements that are non-trivial is 2k, and it's the negative of 2k minus 1. Why? Because 2k minus 1, 2k will tell me take the odd row here and take the next, don't take the diagonal. This would be 2k minus 1, 2k minus 1. Don't take the diagonal because this is 0. For an antisymmetric matrix, the diagonal has to be 0. Okay, so the diagonal is always 0. We are never interested in the diagonal. So here I have the diagonal is 2k minus 1 to k in any such block. So here it would be k equals 2. But in general, you take the first, which is 2k minus 1 to k minus 1, diagonal 0. But if you take 2k minus 2, it will be this number. Okay, so in this case, this is actually minus lambda k. That's the numbering. So this is how I can be selecting it. So now if I consider the quadratic form, g tilde lambda g tilde, then what do I get? I get the summation over jk. Well, maybe let's do it consistent. J1, J2 from 1 until 2L, and then lambda J1, J2, G tilde J1 times G tilde J2. Okay? But now we said that those are the only matrix elements that are non-trivial are of this form for k equals 1 until L, because this is the only matrix elements in this block form. So let's continue. I can now restrict the summation to k from 1 until L, not to L. Then I will have lambda 2k minus 1, 2k, g tilde 2k minus 1. It's the same indices, j1, j1, j2, j2. So 2k minus 2, and then it's different here. And you see how it works. The Grassmann numbers are somehow implementing that the diagonal drops out, because if I would have twice g2k minus 1, g2k minus 1, it's g tilde 2k minus 1 squared is 0, right? So they have to drop out. Okay, and then we continue. Plus lambda 2k minus 1 g, and the same one as the first index, so that's why like this. And here you cannot make a mistake if you're just putting in just. So here I know that this is correct because I'm just looking at the sum like this: first index with first index, second index with the second index. Yeah, so this is correct. And if I continue like this, I can do the swap. So what do I get? I get k equals 1 until L. And now lambda 2k minus 1, we can put it here. So I get lambda k, and I would like to have g2k minus 1. Okay, let me write this out. g2k minus like this plus minus lambda k. Why? Because of this minus. Okay. So the 2k minus 1 have a minus, which means I will need here a minus. And the other matrix element is the minus of this one, so I get a plus. So lambda k, g2k minus 1, tilde. So. Okay, so I can finish the calculation here by saying that this is 2 times k from 1 until L, and minus 2 lambda k, and then I want it to be ascending, so it will be increasing g2k tilde, and it's exactly this stuff. So I get this computation here. Okay, and this we are getting for this convention of the matrices, which means that we can define, I was a bit rusty in the first talk, but now we can start defining conventions that when we will consider quadratic forms, then it's better to consider quadratic forms of this form. Whatever, not skewed. So we just redefine the matrix to include a factor 2 if you wish. So then I will have outside a factor 2. And we can also search for orthogonal matrices onto L. And then you can always write your matrix to be qt lambda q. And that will be my matrix here, which means that lambda I can always put into this block diagonal form k equals 1 until L, and 0 lambda k minus lambda k here. This is a k. Good, which means that I can always write this now as a product 1 plus okay. Let me not do it step by step. I think we will reveal that there was a typo in it. So this is the exponential of 2 cancels, minus is switched, so different convention, sign convention. So if you want lambda k to be positive, you need an O matrix. If you don't care lambda k in purely imaginary, then you can put an SO matrix. You don't care, but it's just defining what lambda k is with a plus minus. So here we have those symbols with a plus, which means the 2 will cancel, the minus will not be there, and I will have only the sum of k from 1 until L, lambda k with a plus, g tilde 2k minus 1, which is the point of this video, and g2k. Yeah? So k, 2k minus 1, 2k. That's the exercise. Now, the product is just taking the product of exponentials here. Yeah, which means that only with this convention, only in 1/2 and 0 lambda k minus lambda k 0 in the convention here, we will get a product. So again, a product symbol because commuting, 1 plus lambda k with a plus g2k minus 1 tilde g2k tilde. So to recap, there was probably a mistake somewhere down the line when I was writing this with a plus, which means I should be defining this lambda matrix to have a plus sign. So where do we have the lambda matrix defined? Well, let's assume that the lambda matrix is defined with a plus here. So it should be a minus here. Minus here. Okay, and when we do this, everything is going through the way we were saying here. We will get a plus and a minus here. And then summarizing, we will get this form here. This plus is here, and this 1/2 is making sure we have it here. Okay.